David Cooper with Flack and Kurtz. We had the distinct privilege of working on both the core and shell with Renzo Piano and FX Fowl and the development team of Forest City and the New York Times, as well as collaborating with Gensler on the interiors. And I just, over the years, working with many different projects with many different clients, owners, each takes on its own personality. And as Hussein mentioned, the New York Times core philosophy of being innovative and looking to make this building something unique and different, improve the environment for their employees, really look at energy efficiency. They allowed us to really be creative and collaborative and push the envelope of what's accepted here in New York City. Today, underfloor air systems, as an example, while not maybe perhaps as sexy as the daylighting and the shades and things, but it was not a commonplace system in New York City when this building first started design. There are two other towers being built with underfloor air now, but they weren't in design yet, and this client, this owner, was willing to go out and explore it, evaluate it, and implement it, and it's to a lot of credit that they can end up with a system and the quality of the building that they are. The way the building is configured, it is a tower. The top half is a spec office space, which Forest City Ratner is responsible for, and they were not as willing to go out on that limb in the marketplace as not being an owner-occupied facility. So that was going to be a conventional overhead air conditioning approach. The New York Times have the bottom half of the building. It'll all be underfloor air, the entire podium for the newsroom as well as the office floors. And beyond the underfloor air systems, there are many other energy efficiency measures that are going into both base building and the tenant fit-out, the interior design, to achieve what will be about 20% better performance than a modern code-compliant energy efficient building. One of those aspects of the job is a cogeneration plant, which wasn't done in New York City for about 20 years. The first one being 140 West 40, being 11 West 42nd Street. They have a critical business operation that has a steady state load, and they were willing to explore, despite the protests of Con Ed and the rigors of not having done one of these in the city in many, many years. They're willing to explore and implement a cogeneration plant because it was able to achieve a 90% efficiency on the power and cooling required by those critical systems. The indoor environment quality was always foremost in the minds, and in addition to energy efficiency savings, the underfloor air system certainly helps improve the indoor environment of the space, both in terms of the cleanliness of the air in the occupied breathing zone, the individual controllability of the air conditioning of the environment and immediate workstation, and as well as ASHRAE, one of the governing engineering societies, now recognizes because the clean, fresh air is delivered right to the occupant, you actually can provide less fresh air than otherwise required by an overhead system, thereby further increasing the energy efficiency of the system and or the indoor environmental benefit of providing a standard amount of outside air. For these floors, the cruciform is hard to see, but it's outlined here of the perimeter building. This is the core, and there's a loop duct around the core that takes air from a central core air handling unit, which would be typical for any most modern office buildings today with a floor-by-floor air conditioning unit. It takes that air and distributes it out to a loop duct under the floor, which is really not a duct, but a series of partitions segregating a pathway under the floor for that air to travel. Where the cruciform extends out from the core, we initially thought we needed to extend some fingers out to make sure the air got out to pressurize all aspects of the floor. And one of the things about an underfloor air system, unlike an overhead system, we have to look at the ductwork and how it lays out and its efficiency. The key to an underfloor air system is really how you get the air into the floor and how the air fills up that floor so it comes out uniformly across the entire floor. A quick cross section. Floor-to-ceiling glass. These are the ceramic tubes on the perimeter, which do a great job of providing some external shading. So while the light comes in, some of the solar heat gain is kept out. The air fills up the raised floor plenum. It rises up vertically to a ceiling plenum where it's returned back to the core. At the perimeter, we have a little device to draw the air and help force it up over the glass during the cold of the winter and during the heat of the summer. And in the interior, you saw on one of Rocco's slides a little scroll diffuser, which passive device and has no dynamic or required control or maintenance. It's up to the user to adjust it if they deem it necessary. So basically, the air rises vertically upward, almost an operating room in reverse, and then goes out at the ceiling. Along the way, it picks up the contaminants in the space. People bring dirt in from the outside, they breathe and exhale contaminants, and all of that dirt in the space is taken straight up and out of the occupied breathing zone, making a very comfortable, clean environment in the occupied level and a warmer environment above. Well, we did a lot of computer modeling of the system to make sure everything would work fine, and along with that model, we also did mock-ups, other mock-ups than the one they're talking about, to actually test the results in a climate lab, as well as going on tours and brainstorming sessions, bringing in other experts and from construction and design experts to really make sure we nail down all of the aspects and the constructability of the system, being that it will be the first high-rise office building constructed in New York with underfloor system. But this computational fluid model, a computer simulation of the space, up here shows a typical overhead system with complete mixing, so it's uniform conditions from floor to ceiling. And here shows the stratification you get even in a 9-foot nominal ceiling, where it's cooler and comfortable in the occupied zone and gets warmer as you approach the ceiling. One of the keys to a proper design, you notice that this is the ceiling plenum below, in red. The blue is the actual floor plenum of the cool air, and these are the air coming up out of the diffusers into the space, and again it gets hot up at the ceiling. The resident time of the air under the floor is what's really paramount in the design, and to make sure that you don't get, it doesn't take too long for the air to go into the floor, and once it gets into the floor, to get out into the space. What we did, and we also modeled that floor plan to make sure that was not going to be the case. And while intuitively we believed we needed these little extensions from this core loop to help the air get out to this remote perimeter, what we actually found is that by jetting the air out there, we created currents under the floor. And that created, the air actually circles and circles and circles before it loses that velocity and comes out of the diffuser. And it warms up because of the heat below the floor. It's just an uninsulated concrete slab separating a warm plenum below that might be 80 to 85 degrees with the air under the floor that might be at 65 degrees. So it gets warm very quickly. So the key is to make sure that the underfloor air is set up so it's a uniform temperature and duration of time under the floor before it comes out. Similarly, we have areas of conference rooms and other things where we have slab-to-slab construction for acoustical privacy, and that creates shadows behind those obstructions to the plenum floor. So again, it was critically important to make sure we had the underfloor air plenum designed properly, and here we found out we did need some fingers to extend some things out. So while it's a ductless system per se, there is a minimal amount of ductwork going to the floor to ensure that that environment is actually properly distributed, and the space then actually takes care of itself.